Assalamu alaikum. In a previous video, we have defined multiple integrals, or in particular, double integrals, such as this dx dy, when this d is a rectangular region, such as this. It's a rectangle. In this video, we extend this definition so that this region can be non-rectangular, such as this. Well, a region such as this means that it is enclosed by a curve. That is, it is bounded, enclosed region. And to do that, we first need the notion of a null set. It's null set. So let's start. Okay, let's give the definition of a null set. We here consider only two-dimensional case, but arbitrary dimensional case is very similar. So A is a subset of the two-dimensional plane, is called a null set if the following condition is satisfied. So this is the definition. First of all, there exists some open rectangular regions. That is AI, BI. So this is an open interval times CI, DI. I is 1 to up to R. So this is a finite number. So this is something like this. Since it's these are open regions, so the boundaries are not included. So something like this. So this is AI, this is BI, and this is CI, and this is DI. Okay, so this is LI. Okay, so first of all, a finite number of such open regions exist such that A is a subset of the union of these open rectangles. Okay, so this means L1 union, L1 union, L2 union, and so on, union LR. And the sum of the areas of these rectangles, I from 1 to R, the area of this rectangular region is this, BI minus AI times, this times is a bit confusing, so just write like this, DI minus CI. So this is the area of Li is less than epsilon, where this is arbitrary for any epsilon that is positive. So if such a finite number of open rectangular regions exist for A, then we say this A is a null set. Okay, that's fine with the definition, but what does it mean really? It means, so since this epsilon is arbitrary, as long as it's positive, then it can be very small. It can be arbitrarily small. So that means if this inequality holds, then the sum of these rectangular regions can be arbitrarily small. So, and also this condition indicates that this set A can be covered by the union of these rectangular regions, which are very small. I mean, it can be arbitrarily small, so that means the area of this A should be arbitrarily small, or even 0. So that's what a null set means. In other words, the size of the null set, in this case, the size means essentially the area of this set, it can be ignored. It's arbitrarily small. So that's the meaning of null set. But it should be distinguished. It should not be confused with empty set. Okay, empty set is a set that contains nothing, right? But a null set can contain something. For example, a set consisting of a single point. It is a null set because the area of a single point is 0. And so we can see that these conditions can be satisfied. In fact, we can find a single open rectangular region that contains this single point, and the area of this rectangle can be arbitrarily small. So this is a null set. And another example of a null set is a line segment. So straight line segment. So the line segment, it has the width of the line is 0, right? So for example, it can be covered by a single rectangle. And the width of this rectangle, or you can say height of the rectangle, can be arbitrarily small. Therefore, this line segment can be covered by a finite number of open rectangular regions. Therefore, it is a null set, although it is not an empty set. Okay, it is a null set. And also, if we have a finite number of null sets, like A1, A2, A3, and so on, and let's say AN. If these are null sets, then the union of these sets is also a null set. Is a null set. Next, we want to show that the graph of a continuous function defined on a closed interval is a null set. So let's say if we have a continuous function defined on a closed interval. So in that case, this set, so this graph, is a null set. But before the proof, let us give a simple theorem that comes handy later. That is, first let D be a bounded closed set in the n-dimensional Euclidean space. Bounded closed set in n-dimensional space. And let f be a continuous function on this set D. And we write f of x, and x is a vector actually. So it's n-dimensional, so there are n variables. So if f is a continuous function defined on a bounded closed set, then f of x is actually a uniformly continuous on D. On D. So this part, uniformly continuous, is important. We had a very similar theorem for the univariate functions, but the same applies to multivariate functions. By the way, what is uniformly continuous? Remember? So, okay, so let's review the definition of a continuous function on a set. Okay, so f of x is continuous on D. So this is just ordinary continuous function, okay? So what is the definition of this? Definition. So that means for all points in D, for any epsilon that is positive, there exists a positive delta such that for all, let's see, y in D, we have the following implication. That is, if the distance between x and y is less than delta, then it implies that the difference between the functional value at x and at y is less than epsilon. So that's what this means for this function to be continuous on this set D. Okay, so the point here is for all x in D is here and for all y in D is here. So they are separated. So what this means is that this delta can actually depend on the value of x. So depending on where, so let's say, suppose this is D, depending on where the x is, so maybe x is here or x is here, x is here, the value of this delta such that this implication holds can be different. So okay, so this is what this continuous means. Continuous functions mean. On the other hand, if f of x is uniformly continuous, so this part is important. So the definition of uniform continuity is the following. For any epsilon greater than 0, there exists delta that is positive, such that for all x and y in D, the following implication holds. If the distance between x and y is less than delta, then the difference between f of x and f of y is less than epsilon. Okay, here both x and y are here. So that means the value of delta does not depend on the value of x. So that's what we mean by uniform continuity. Okay, so the value of delta doesn't depend on where this x and y are. So this continuous condition is uniform throughout this set D. Now let us prove the following lemma. Let's see. So let y equals to phi of x be a continuous function. Shown on a closed interval. So this is a univariate function. Let's see, between a and b. Then its graph. By the way, the graph, let's name it as gamma. The graph is the set of points x and y such that y is equal to phi of x. And x is between a and b, including a and b. So this is a set of points such that this and this hold. So this is the graph of this function. Then this is a null set. Now let's try to prove this. Okay, so the proof. First of all, this is a continuous function defined on a closed interval. Therefore, it is also uniformly continuous. Okay, so since y equals to phi of x is uniformly continuous, so according to the definition of uniform continuity, we have the following. For any for any epsilon, there exists a delta such that for all x and x prime in this interval, we have if x minus x prime is less than delta, then the difference between phi of x and phi of x prime is less than epsilon over b minus a. So since epsilon is any positive real number, epsilon over b minus a is also any positive real number, right? So we can always find some positive delta such that this holds. Next thing we do is to partition the interval. Okay, so x and y. So this is what we do. Suppose this is a, suppose this is b, and we have some continuous function here. So we partition this interval into small pieces. So these are subintervals. Let's say this is a0 and this is a1, this is a2, and so on. And b is, let's say, a r. Okay. And so we make this partition sufficiently fine so that any subinterval, this is the width of any subinterval is less than this delta. Okay, so for any I that is 0 to let's see, r minus 1, we have ai plus 1 minus ai is less than delta. So we make this partition so that this holds. Okay, so these intervals are so fine that this is also true, always true. Okay, now let us define capital Mi as the maximum value of the function in the interval between ai and ai plus 1, and lowercase mi as the minimum of this function within this subinterval. Okay, since this is true, the width of the subinterval is less than delta, we always have this this inequality. Okay, so that means the difference between capital Mi and lowercase mi is less than epsilon over b minus a for any I. Okay, so this is for I from 0, 1 up to r minus 1. Okay, so mi minus mi is less than epsilon over b minus a. Okay, next we define open rectangular regions, Li as the open interval. So ai minus rho. Rho is a positive constant. ai plus 1 plus rho. So this is a Cartesian product times, wait a minute, it's bm mi minus rho, uppercase mi plus rho. And rho is an arbitrary positive constant. So what this means is that for this graph, so suppose this is ai and consider this this subinterval, then we make this something like this. It's a rectangular region. So this x coordinate is ai minus rho. Wait a minute. So this is a bit less than ai, a bit more than ai plus 1. And so this is the maximum value in this interval, and maybe this is the minimum value of the function in this interval. But rho is a positive constant, so this value is lowercase mi minus rho, and this is uppercase mi plus rho. So we consider such a open rectangular region. We call it the multi-interval because we have one interval here on the x-axis, another interval for the y-axis. So this rectangle is a Cartesian product of these two intervals, so it's called a multi-interval. Anyway, we define such a rectangle for each sub-interval here. Okay. So for each of these intervals, we define such, actually they are overlapping rectangles, like this, and so on. That is, we cover this graph by a set of rectangles. It's a finite number of rectangles. Okay, so if we define the rectangular region as di, di as ai plus 1 times and mi. So this is a closed interval and closed interval. So this is the rectangle. Okay, let's. So this will be the rectangle here. And if this rho, the value of rho converges to 0, goes to 0, then the area of this Li converges to the area of di. Okay, for convenience, let's write mu of Li as the area of this open rectangular region Li, and mu of di is the area of this closed rectangle di. Okay, so if we take rho, the value of rho to 0, then the area of Li converges to the area of di. So that's what we meant. And now, as we have seen from this figure, if we take the union of these Li's from I varying from 0 to r minus 1, then that union covers the entire graph. That means gamma is a subset of the union L1, L0 union, L1 union, and so on, L r minus 1. And the sum of the areas, the sum of the areas of these rectangles. So area of the rectangle is ai plus 1 minus ai times mi minus mi. So this is less than the sum of 0 to r minus 1, and this is the same part, ai. So this one is less than this, epsilon over b minus a. And this is a constant, so we can take out of the summation. And this one, if we expand, we have something like this. So a1 minus a0, and a2 minus a1, and so on. And in the end, we have a r minus 1, right? But this A1 is cancelled by this A1, and this A2 will be cancelled by another A2, and so on. And everything will be cancelled except for this one and this one. So that is epsilon b minus A and AR minus A0, but AR is just B and A0 is just A. So this and this will be cancelled, and we have epsilon. So that means this finite set of open rectangles cover the graph, and the sum of the areas of these rectangles is less than epsilon, where epsilon is any positive real number. So therefore, gamma, by the definition of the null set, gamma is a null set. And we are done. Okay, next we extend the class of functions that can be integrated to include non-continuous functions. So here's the theorem. Okay, let f of xy, we consider only bivariate functions in this case, be a bounded function on a rectangular region D, which is AB times CD. And let A, which is a subset of D, be a null set. And if this function is continuous on D set minus A, so that is, this function is continuous everywhere on D except for A, which is a null set, then f of xy is Riemann-integrable. On D. So what does this mean? We are considering a function that is defined on a rectangular region. Let's say this is D. Okay. So this is x, this is y, and this is A, this is B, this is C, and this is D. But this function may not be continuous everywhere on this region D. But there are some points, let's say it may be a curve like this, or maybe it is a set of points, isolated points, which are, each of which is a null set. So the union of them all is also a null set. Okay, so this function f of x and y is continuous everywhere except for these null sets. Okay, this is a null set. So except for these points, this function is continuous. Then this function is still Riemann-integrable. But in order to prove this theorem, we have to recall the definition of Riemann-integrable. Okay, what is it? So first we define the upper Riemann sum and lower Riemann sum, and they converge to the same value as we refine the partition of this rectangular region. So that is, if we write S delta as the upper Riemann sum with partition delta, and lowercase s delta as the lower Riemann sum with partition delta, then this difference should be less than epsilon, where epsilon is any positive real number. Okay, if we can show this, this is upper Riemann sum. And this is lower Riemann sum. So if this difference converges to 0, then we have a function that is Riemann-integrable. Well, the proof is technically a bit involved, but the idea is very easy to understand. So in order to define the Riemann sums, we first define some partition, right? So we divide these intervals into small pieces, subintervals. Then we classify each of these small rectangles into two classes. One that contains the null set, any point in the null set A. Okay, so let's see. Let's change the color here. So maybe this rectangle, these yellow rectangles may contain some point in the null set. Okay, and maybe this one, maybe this one. And if we ignore those yellow rectangles, then each of the other rectangles is just a rectangle, and the function is continuous on those rectangles. Therefore, they are Riemann integrable. That's okay. And what about these yellow regions? In each of these, since they are null set, then they can be covered by a finite number of open rectangles, and the total area of which converges to 0, right? So basically, the area of this yellow region can be made to arbitrarily small value. So therefore, they converge to 0, and the volume on these the area of these yellow regions in total will be 0. Therefore, they do not contribute to the Riemann sum, and therefore the upper and lower Riemann sums converge to the same value, and the function is therefore integrable. And that's the idea. Okay, we prove in 3 steps. Step 1. Since f of x and y is bounded by assumption, then that means there exists some real number, positive number m, such that for all point in D, the absolute value of the function is less than m. So that's the meaning of bounded function, right? So the function value is bounded by m. And also, since A is a null set, there exist L1, L2 open rectangles, LR, such that A is a subset of the union of these rectangles. Okay, and the sum of the areas of these rectangles, area we represent by mu of LK. The sum is less than, it can be made less than any arbitrary positive number. So in this case, let's say epsilon divided by 4m. Okay, and this mu of LK is given by this A. A should be B k minus AK times dk minus ck. So each of LK is an open rectangle. So defined by the open intervals AK bk times ck dk. Okay. So from this, we know that the area is given by this. And step 2. Step 2 is we define a set D prime by D set minus union of all L's. Okay, so this is intuitively this is something like this. So we have D here, this rectangle, and suppose this is A. Okay, since it's a null set, we have a set of open rectangles that cover collectively cover this null set, right? So these are L's, okay, like L1, L2, and so on, up to LR. And so we remove the union of these red rectangles from the set D, and that is defined as D prime. Then, if we define D prime like this, then, by the way, D is a bounded closed set, right? And then D prime is also bounded and closed. Okay, is bounded and closed. Why is it so? Okay, this set difference can be written as this. D set minus union of LK can be also written as this. Intersection between the union, D and the union of the complement of the union. Okay, and now each of LK is open. So LK is open. It's an open set. Then the union of LKs is open. Okay. Then its complement is closed. Remember the definition of the closed sets? A set is closed if its complement is open, right? So therefore, the complement of this is of course this, which is open. Therefore, this one is closed. Okay, now D is closed. Okay, D is closed. And therefore, the intersection between two closed sets is closed. R is closed. Why is it so? If we take the complement of this, okay, let's take the complement of this, ULK, okay, let's take the complement. But the Morgan's law, this is D complement, union, and the complement of this is union of this, right? And we know that this is open. Since D is open, D complement is open. This one is open. This one is open. And the union of open sets is open. And therefore, the complement of this is closed, which is this. Now, this D prime does not include the points at which the function is not continuous. That means the function f of xy is continuous on D prime. which is closed. Okay, therefore f of xy is, since it is continuous on a closed set, then it is uniformly continuous. Uniformly continuous on D prime. So according to the definition of uniform continuity, there exists some delta, which is positive, such that there exists, not for all, exists delta, such that for all points in D prime, let's say xy and x prime, y prime in D prime, such that if the distance between these 2 points, so distance between xy and x prime, y prime, less than delta. If you prefer, you may write like this, minus x prime, y prime, delta. If this is the case, then the difference between the functional values is less than, let's say in this case, let's put 2 mu d. Okay, and of course the area, this is the area of the region D. Mu of D is b minus a times d minus c, because it's a closed rectangular region. So if 2 points are close enough, that is closer than delta, then the difference between the functional values can be always made smaller than this value. And step 3. Now we consider the partition of the region D. Okay, so let's consider the partition. So this is D. And suppose this is a null set A, on which the function is not continuous. Okay, now we consider the partition that is fine, sufficiently fine in the following sense. So let's see. So this partition is labeled by I and j. So this is dij. So I is in this direction and j is in this direction. So that in any of these partitions, any 2 points within one sub multi-interval, the distance between these 2 points is always less than delta. The delta is the one we found here. Okay, so that means the value of the functional values within each of these smaller rectangles is always less than this value, epsilon over 2 mu of d. So that means, so that's what we mean by sufficiently fine partition. And we also impose the condition on this partition so that those rectangles LKs, these are, where is it? Okay, so LKs are defined by this open rectangle. So these points are also the points of the partition delta. Okay. So one of, or maybe it can be something like this, but those grid points, some of these grid points are also the grid points of the defining rectangles of the covering open rectangles of this null set. Okay. Then we consider the Riemann sums. Okay. So this partition is delta. Consider partition delta. Okay. And uppercase S delta is the upper Riemann sum, and lowercase s delta is the lower Riemann sum. So if we take the difference, it looks like this. So let's say I from 0 to n minus 1, j from 0 to n minus 1, and capital Mij minus lowercase mij times the area of the small rectangles, dij. Okay, and of course this uppercase Mij is the supremum of the functional value on dij, and lowercase mij is the infimum of the functional value on the region dij. Okay, now we split this sum into two parts, S1 and S2. And here S1 is the sum over all those dij's that contain the interior points of the null set, such as these green rectangles in this picture. Okay, maybe this one too. Okay, and S2 is everything else. Now let us evaluate these sums. Okay, first S1. For each term in this summation S1, we have mu, wait a minute, first of all, we have Mij minus Mij is less than 2m, less than or equal to 2m. By the way, this capital M here, without any indices, is the bound of the functional value. Okay, where is it? This one, this M. Okay, so the maximum value minus the minimum value should be less than this, right? And because of the way we chose S1, these di's involved in this sum S1 is a subset of some LKs. LK is covering open rectangles of the null set. Okay, so that means within S1, the area of dij, of course dij is the term involved in this sum. Okay, this is less than the area of LK for some LK. Okay, so that means this sum S1 is less than or equal to 2m. So because of this is less than this, we have 2m here, and the sum of k's and the area of LK. Okay, and but this is smaller than less than 2m less than epsilon over 4m, right? Because of where is it? This. You know, the sum of the areas of these covering open rectangles can be arbitrarily small. In this case, it can be made smaller than epsilon over 4m. Therefore, we have this inequality. So this m be cancelled, this be cancelled, and we have epsilon over 2. Next, as for S2, because of the uniform continuity, we have this inequality. So this capital Mij minus lowercase mij is less than this value, epsilon over 2 mu of d. So this is less than, so sum over I and j, but this summation is only limited to those ij's that are involved in this S2, okay? So epsilon over 2 mu of t and mu dij. Okay, so this is constant, so we can take out of the summation. Mu d. Okay, and mu dij. Again, we insist that this summation is not for all ij's, but only for those that are involved in the sum S2. So if we add all this is the area of d prime, right? So this is the area where S2 is defined. So this is epsilon 2 mu d times mu of d prime. And of course, d prime, the area of d prime is less than the area of less than or equal to the area of d, because d is a superset of d prime. So we have epsilon 2 mu of d times mu d. So we can cancel this to have epsilon over 2. So combining S1 and S2 plus S2, we have epsilon over 2 plus epsilon over 2, which is epsilon. But epsilon was any positive real number. Therefore, we have proved that the Riemann sums, upper Riemann sum, and lower Riemann sum, they converge to the same value. And we are done. We are now ready to define the Riemann integral of a function defined on a closed region bounded by a curve. But before that, we need to specify what we actually mean by that closed region bounded by a curve. So here's the definition. First, we define a Jordan curve. Definition. Jordan curve. So let phi be a function from the closed interval between 0 and 1 to the two-dimensional point. A continuous map such that phi of 0 is equal to phi of 1, and the restriction. So if we restrict this to the semi-open interval, so not including 1, but including 0, is injective. So it's 1 to 1. Then the image of phi is called a Jordan curve. Okay, so what this means is the following. For example, this can be a Jordan curve. Okay, so if the map at this point corresponds to phi of 0, and if we increase the value of the variable to 1, and the value of phi 1 coincides with the same point as phi of 0, and this is injective, okay, because phi of t equals to phi of t prime, then this means t is equal to t prime, right? What this means is that no two values of t and t prime coincides at the same point. Okay, so maybe it's easier to see what's not a Jordan curve. Okay, so this is not a Jordan curve because this point can be achieved by two different values of the parameter. Okay, so if we start from here, at one point we have this point, and if we just continue, and then we comes to the same point at some value of t, before we come back to the original starting point. So this is not injection because two different values of t can have the same point. So it's not a Jordan curve. And if we are given a Jordan curve like this, so suppose we have this plane, two-dimensional plane. In this plane, if we have a Jordan curve like this, there is a particular property of the Jordan curve, of any Jordan curve, is that this separates the two-dimensional plane into two parts, splits the entire region into two parts. That is interior and exterior. This seems trivial, but it requires a proof. But we don't give a proof, but we just accept that it as a truth. So this is called Jordan theorem and Jordan curve theorem. And you may want to look up Wikipedia for that. So if we have a Jordan curve, we can define its interior and exterior, and the union of the interior of the Jordan curve and the Jordan curve itself defines a closed and bounded region. Okay, closed and bounded region. And this is called Jordan region. Jordan closed region, actually. Or closed Jordan region, whatever. Now we can state our goal of this lecture. Here's the theorem. Let f of xy be a continuous function on a bounded closed region. Let's call it D. Then f of xy is Riemann-integrable. Actually, the proof is quite easy. So, proof. So let's say the function is defined on some bounded closed region, and we define a rectangle that includes, that it's a superset of that region D. Let's call it R. And we define, so the function f of x is defined on this D. Now we define another function that is an extension of the given function. Okay, so we define f tilde of f, x, and y as this. It is the same as f of xy if xy is a point in D. Otherwise, it's defined to be 0. Xy is not in D. Okay. So here, so outside D, this f tilde takes the value of 0. Inside D, it takes the values as same value as f of xy. Now, by assumption, f of x and y is continuous on D, therefore f tilde is also continuous on D. Okay, so that is f tilde f x and y is continuous on R except for the boundary of D. Okay, so this means boundary of D. And this f tilde is, of course, continuous on outside of D, right? So forget about D and its boundary. Because it's always 0 everywhere, then it's continuous, right? So this function is continuous everywhere on R except for the boundary of D. Maybe it is continuous sometimes, but not always. It's not necessarily continuous. But the boundary, let's call it DD, is a null set. It's a null set. Null set. And by the previous theorem, this f tilde is Riemann-integrable. No, it is continuous except for a null set, so it is Riemann-continuous, integrable. And this integral is equal to R tilde of fnxy dx dy. Because outside of D, the value of this function is all 0. So what's remaining is the same as f of xy. So this equality holds. Therefore, the original function f of xy is integrable on D. And we're done. Although we don't deal with triple integrals or multi-integrals in general, the same theorem applies. So if the function is continuous on a bounded closed region, then it is Riemann integrable. I mean, in any dimensions. But that doesn't mean that we can always easily calculate these integrals, so we need some convenient techniques, which we'll explain in the next video. So that's all for this lecture. See you later.